This conference will now be recorded.
So, good morning, students. Today we'll be continuing discussions on wave chapter. Here, today we'll learn the displacement relation of progressive wave, some important definitions which we have already discussed a little bit. We'll just recap those. Then speed of traveling wave, and we'll try to learn about the speed of transverse waves in straight string. So, displacement, as we had discussed this figure, you might be remembering, if a person just give a jerk on the rope which is tied at one end and the other end is at his hand, and if he gives a jerk, we have seen that a kink is produced in the rope or string, and that kink will travel all the way up to the end of the wire, and eventually we'll see this kink is traveling all the way through this wire. While this kink is traveling, in fact, the string is not moving. What is moving is the wave or disturbance through the string or rope, and in that process, the particles of the medium of the rope, they are actually oscillating up and down. So as you can see, okay, and see, this is actually when a wave produced at certain point and it travels all the way through the medium, then that kind of wave is called progressive wave. Progressive means it progresses, okay, which just after production, which travels. So that wave is progressive wave. So what is progressive wave? Wave which travels through the medium. Through the medium. Okay, that is actually a progressive wave. All right. Now the question is how to write down the displacement relationship of progressive wave. To describe, see, if we want to describe a progressive wave, then we have to find out a particular equation or particular relationship between many things like time, space, the displacement, etc. So if we can find out a particular way of expressing the displacement relationship of progressive wave, which will actually describe the wave at any instant of time, and at any position. So that is actually real expression or relation for the progressive wave. So in general, progressive waves displacement due to progressive wave displacement due to progressive wave is expressed in terms of in terms of sinusoidal function. So this we had already discussed somewhat. We are just discussing once again since we have to learn it very nicely. So sinusoidal means it can be either cosine or sine. I'm writing a sine of kx minus omega t plus phi. Okay, so this is a form of expressing the displacement relationship of progressive wave. So how do you understand this particular relation between y, x, etc.? So this is actually displacement of the particle in the medium. This is displacement of particles in the medium. Okay, this is the displacement, and you can look one thing. This is y, whereas it is a function of x. What does that mean? That means this displacement of the medium particle, or the displacement of the particle in the medium, is a function of x and t, that is the position and space. So this is a function. Displacement y is a function of space, that is x, and time. Okay, one more thing is that here the displacement of the particle is in the y direction, while the wave is actually progressing or traveling in the x direction. So what we can say from here? We can say the wave is transverse in nature. Wave is transverse in nature. So the wave is transverse in nature because the displacement of the particle is along the y direction, while the wave is progressing in the x direction, as you can see from the figure. Okay, and what else it is giving? See the displacement, how the particle is at particular instant, where the particle is a- at an instant, that is actually described by this particular equation. So this is one type of equation. Now you can write this as a cosine also. You can write this as cosine also. So yxt, one can write, instead of writing sine, one can write cos, one can write this also. So this is also another way to express the displacement. And surprisingly, if suppose this is y2, or let me take some other as y1, y2. If suppose y1 xt is a cos of omega t or kx minus omega t, and y2 is b sine kx minus omega t. If this is the case, if they are, if each of them indicates or represents the displacement of the particle, then their linear combination also will be able to describe the displacement of particle of medium or a particle in the medium. Okay, so in that case, see, now we'll learn one good thing over here. Suppose you have y1 x and t a cos of kx minus omega t. Just a minute, I'm getting an important call. So suppose obviously these expressions are actually periodic, and we have already learned when we have learned SHM. So this express is the uh, displacement in SHM, simple harmonic oscillations. So if this is one solution of the differential equation of SHM, and if another one is this one, suppose B cos of, sorry, let us say sine omega t. So if you take the combination, that will also give you a solution. So that can be actually shown. In that case, actually the displacement will not neither be A or B. Let us take the combination, linear combination. Suppose y is equal to y of x and t is equal to y1 plus y2. So let's say this is a cos of kx minus omega t plus b sine kx minus omega t. So this term is called amplitude, and the argument is called actually the phase. Okay, phase constant. And both the waves are actually traveling in the positive x direction. Okay, so in this case, what is the amplitude of this particular displacement? So how do you express that? So you can do one thing, you can just take this A as sine phi, B as cos phi, and then write it down. So let us see what happens. Let us take this first. So B sine kx minus omega t into cos of phi plus sine of phi, this term, into cos of kx minus omega t. So if you use the trigonometric like identity, then this can be written as sine kx minus omega t plus phi. Okay, and what is the, okay, let us say this is a, this is a here, so there will be a over here. So what is this a, what is the value of this a? This can be found out from here if you square them out. Okay, so this will be, and add this two, so a square sine square phi plus a square cos square phi. So this will give you a square is equal to capital A square plus capital B square. So this amplitude will be square root of a square plus b square. So this is how the amplitude changes in that case. And what is the phi? Phi will be actually, phi will be tan inverse a by b in this case. Okay, tan inverse a by b. Okay, so this is the way to express the displacement of pro progressive wave. Once again, I'll just write down this. and tell you which term I'm writing now as cos kx minus omega t plus phi. So each term you need to know this is the displacement of the particle in the medium, displacement, then this is called amplitude, and this term argument, the whole argument is a, actually it is a phase term, phase term, phase term. And what about k? K is actually 2 pi by lambda, which we'll be discussing today. This is called propagation constant, propagation constant, propagation constant, and this phi is called initial phase, initial phase, initial phase. Initial phase means when t is equal to 0, at t is equal to 0. So if the t is equal to 0 over here, so you will get a cos of kx plus phi. So from there you can find out what is the initial phase. Okay. In general, at t is equal to 0, displacement is 0, velocity is 0. So cos of kx plus phi is also is equal to 0. So cos will be 0 at 2n plus 1 pi by 2. This will be the relationship. Okay, so from there you can find out the relationship between k and x, sorry, k and phi. So this is displacement, this is amplitude, this is the phase term where k is 2 pi by lambda, which is called propagation constant, and phi is actually called initial phase. Okay. Now we had already discussed somewhat different important terms like amplitude. What is amplitude? What is phase? What is time period? Those things we had already discussed, but we'll still just touch a little bit upon that. As a recap. So what is amplitude? Amplitude actually is the maximum displacement, maximum displacement suffered by particle in the medium. Okay, about the mean position, obviously. So that is actually displacement, and it is denoted in general small a or capital A. It is denoted. Amplitude is denoted by small a or capital A. Okay, and you can see in this figure the displacement. This represents the displacement. This displacement of the particle. This you can see. This is the maximum displacement. So the maximum displacement over here is A, and that is actually called amplitude. Okay, so this is amplitude, maximum displacement. all right, and it is plus or minus a. In case of sinusoidal wave, if I write sine, so since it is a sinusoidal curve and sine has a value maximum value either positive 1 or negative 1, that's why the amplitude will be either plus a or minus a. That is the maximum displacement. In this figure you can see there is a short arrow, sorry, let me go there. There is a short arrow, you can see this arrow. This is actually denoting the point where the displacement is maximum, that particular point of the wave. So displacement of the particle is maximum at this place, and this is called crest. This point is called crest where the amplitude is maximum, CREST, crest. And this is maximum in the positive x direction, sorry, positive y direction. That can be maximum in the negative side also. This is called trough. So crest and trough, TROUGH, trough. So these are two things here. And you can look in case of progressive wave, this peak actually progressing in the forward direction, in the positive x direction. See the arrow has displaced from the first figure to second figure, then in the third figure it has displaced in the positive x direction. If you look the first arrow and the fifth arrow, you can understand very well that the wave has traveled from the point which I have shown in the past. From with respect to that, the fifth peak or the crest is actually in the right hand side. It has progressed in the right hand side. So from here also you can understand about the progress of the wave. So this is amplitude. Now what is called phase? We'll learn what is called phase. The argument of the oscillatory term A sine kx minus omega t plus phi. Kx minus omega t plus phi, this is called the argument of the sine curve, or that function A sine omega t kx minus omega t plus phi. Okay, so that term is actually called phase term, and the phi is called initial phase, as I already had discussed. Okay, so phi is actually initial phase. Now phase, actually what is phase? Phase can give you the state of motion at each instant and each time. Phase gives the idea of phase gives the idea of the state of the motion or oscillation in this case at any instant of time, and at any position. Okay, so phase will give you the state of motion. Now we'll go to, okay, this is phase. Now time period. Time period, as you know, it is the time that a wave takes to have a full cycle of oscillation. The time taken by a wave which undergoes a complete cycle of oscillation, or the time which is required for a complete cycle of oscillation, is called the time period. As you can see, if I start from T1 here, from here all the way up to here, this is the complete time period. Or if we start from here, so from this point to this point, a complete oscillation. So the time interval, if it is T1, if it is T2, then T2 minus T1, it will give you the time period, total time period. So time period is the time which an oscillator takes to have a complete oscillation, that is called time period. Okay, so that is actually called time period. I'll write it here. Time period is the time that an oscillator takes to have a complete oscillation. Complete oscillation. Okay, so this is our time period. Now what we'll do, we know frequency. Frequency is the reciprocal of the time period. So time period means in a particular time of instant of time, there will be only one full cycle. During this time period, there will be only one cycle or one complete oscillation. But frequency is the number of oscillations per second. Number of oscillations per second. So time period is actually denoted by capital T, and frequency of oscillation is denoted by nu. This is directly proportional to 1 by T. Okay, frequency of oscillation. All right. Now we'll learn a relationship between wave velocity, frequency, and wavelength. Oh, wavelength, I have not told you. Let me tell you what is called wavelength. Sorry. Wavelength means actually the distance along the direction of the wave propagation. See, if I have a crest I have tau. So crest and tau. So one crest and one tau. This will constitute a complete oscillation, and or a full cycle of oscillation. And the length, linear length in the medium, a length like which covers the full cycle. Okay, the length. See this much is particular length. This much is another particular length. So the total wave, a total length, a complete wave takes is actually called the wavelength. And wavelength is actually denoted by lambda. So what is the wavelength here in this figure? The distance or the length of the full wave, a complete wave. This is called wavelength, the complete wave. Length of complete wave is known as wavelength. So here the lambda can be this one. This is lambda. Okay. So lambda means wavelength. So we have learned time period, frequency, and wavelength. So there is a relationship between wavelength and velocity of wave velocity, time period, or frequency, etc. Okay. So we have a particular relationship between wave velocity, frequency, and wavelength. Let us find out what is that. So we know wave velocity means distance by time. So wave velocity. Wave velocity means distance that a wave travel in a particular time period. Let us say some time itself. Okay. So distance by time, we can take one thing, we can just do one thing. We may not know the whole the distance, but at least we know the distance for a complete cycle, that is lambda, and the time taken during a complete cycle is the time period. Okay, so we can write lambda by capital T. So it will give you the lambda by capital T if the wave velocity is v, then v by t is lambda, or lambda is equal to vt. Okay, lambda is equal to vt. And what about, okay, let us so wave velocity v is equal to lambda by t. So this 1 by t is again nu. This is nu 1 by t. 1 by time period is the frequency. So we have got a relationship between wave velocity. We have got a relationship so we have got a relationship between or among between wave velocity among wave velocity then frequency and time period. Okay, so frequency, time period, and also with wavelength. So this is the relation. V is equal to nu lambda. This we might have learned in the 10th standard also, but you don't know what is nu, what is lambda, etc. So wave velocity is equal to nu into lambda. Lambda is the wavelength and nu is the frequency of the wave. Okay. Now we'll learn how to calculate this wave, like velocity of wave in a string. Stretch string. How to calculate the wave velocity in a stretch string. Just I need to drink some water. Just 1 minute. So now we'll learn how to calculate the speed or the velocity of transverse wave in straight string. You might be knowing what is straight string. Let me first write the topic. The speed of transverse wave in a straight string. Straight string. Okay. This is the topic now we are discussing. Straight string means suppose you have a string, one end of it is, or maybe both the ends are fastened at two fixed and rigid support such that the string is not slackened, it is properly tightened. So this is called actually a straight string. Straight straight string. So the speed of the wave on a straight string depends on its inertial and elastic properties. So speed of wave on a straight string depends on its inertial and elastic properties. Okay, so what are those factors actually? The speed of transverse wave through straight string is determined by two factors, mainly two factors. Speed is determined by two factors. Speed in straight string. Speed in straight string is determined by two factors. So what are the factors? We'll write those factors are: one is the tension, one is the tension in the string, in the string, and the second is the mass per unit length of the string, mass per unit length of the string. Mass per unit length. Mass per unit length. Okay. So what is the tension in the string? Since it is actually supported in two ends, then it has a tension acting on this, and the dimension of the tension is actually same as the force, that is ml to the power minus 2. Mass per unit length has actually dimension capital M by L. So this is mass per unit length. Now what we can do? Now let us take the ratio of these two, T by M, dimensional ratio. What we will be able to get is this. Okay, that was the dimensional ratio. Now this, if the speed, see the speed has a dimension L to the power minus, speed has dimension L to the power minus 1. Okay, so we can express this V as C into root over tau by time period by M. Okay, so this is actually the speed in transverse. This is actually the velocity or the speed of the wave, transverse wave in a string. Okay, here C is equal to 1. If we put C is equal to 1, this is dimensional quantity, so the speed of the wave can be expressed as So this c is equal to 1, then it will give v is equal to root over t by m. Okay, so this is about the speed, which is the speed of wave, transverse wave in a straight string. Next day we'll see how to calculate the speed of longitudinal wave. We have learned today how to calculate the speed of transverse wave. Next day we'll see how to calculate the speed of longitudinal wave, and then further related things we'll discuss. We'll stop it here for today. Bye.